Welcome, Algebra peeps. Today we are going to take a look at variance and standard deviation, starting with a little comic. Statistics say that religious people live longer, so I practice a different religion every day of the week to be sure I'm covered. Ah ha ha! We took a look at this in the last video. This is variance in the normal curve. So when we have a normal distribution, we will have 68% of our data within one standard deviation. We will have 95% of our data within two standard deviations and 99% of our data within three standard deviations of the mean. So what is this standard deviation and variance all about? Well, before we get to that, we'll just review this notation because it's going to be used a little bit going forward. When we're talking about the population, we use mu to represent the mean and lowercase sigma to represent standard deviation. When we are calculating the mean of the sample and the standard deviation of a sample, that's represented by x bar and S. Let's take a look at a normal distribution. This is your notes, pages 19 to 20. A normal distribution is a very important statistical data distribution pattern occurring in many natural phenomena: height, blood pressure, lengths of objects produced by machines, etc. Certain data, when graphed as a histogram, creates a bell-shaped curve known as a normal curve or normal distribution. These are symmetrical, with a central peak at the mean. 50% of the distribution is to the left and 50% is to the right. The mean and the median are the same in a normal distribution. The bell curve, which represents a normal distribution of data, shows what the standard deviation represents. One standard deviation away from the mean, so this is where we have a population, in either direction accounts for 68% of the data. 34% above, 34% below. Two standard deviations away from the mean accounts for roughly 95%. 47.7 on either side. 99% of the data would be covered by three standard deviations. Sigma notation is used to represent the formulas for standard deviation and variance, and it uses summation notation. So summation is something that is done quite often. There is a symbol that means summation, and that's the Greek letter sigma. This is the uppercase sigma, and it's sometimes called sigma notation. Sigma notation looks like this. This says I'm summing up all of the a sub i's where a takes on from 1 to n. So that's a sub 1 plus a sub 2 plus a sub 3, on and on and on until we get to whatever we define n to be. The I is called the index, the lower limit is 1, and the upper limit is n. This notation tells us to add all the a sub I for all integers starting at 1 and ending at n. So here are a few examples of just how we use sigma notation. Here we're going from 1 to 5 of a sub I. So that would be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. In the second example, I'm adding 2x cubed where x takes on from 1 to 4. So it's 2 times 1 cubed plus 2 times 2 cubed plus 2 times 3 cubed plus 2 times 4 cubed. And they calculate that here. It's 200. The index may start at any integer and must increase to the upper limit of the sigma notation. So here we didn't start at 1, we started at 4, and we're calculating 2n minus 3 where n varies from 4 to 7. So 2 times 4 minus 3, etc. And if you were to calculate that, it would be 32. Variance is the average squared deviation from the mean of a set of data. It is used to find standard deviation. So let's talk about all those components of variance. First, we find the mean. Then we subtract the mean from each value. We find the difference or the deviation of each value from the mean. We square each deviation of the mean. Now, why would we want to do that? Pause, think. Because some of those differences will be positive and some will be negative, and they are just as important whether they're positive or negative, so we don't want them to cancel each other out. So by squaring them, we eliminate that canceling of one another. We then find the sum of the squares and divide by the total number of items. So we're finding the average squared deviation from the mean. Now, this is going to look a little hefty, but let's process together. It includes sigma notation, which is all the items to the right of the sigma. Remember, mean is represented by mu, and n is the number of items. So I'm taking the item, the score that I had, subtracting the mean, squaring it, and then adding all of those up and dividing by n. We're adding each difference of each score from the mean, squaring it, and dividing by the total number of scores. This is finding the average of the squared deviations of the mean. And then the standard deviation is easy once you've gotten variance. Standard deviation represents the spread, and the smaller the standard deviation, the more concentrated the data, and it's often denoted by lowercase sigma. To find the standard deviation, we do the same thing as variance, so A through D are variance, and then we undo the squaring. We take the square root. So this formula, again, is going to look a little hefty because it's a variation formula, but taking the square root. So I'm adding the squared difference of each score, and I'm adding those together, dividing by n, and then taking the square root. So we're going to do an example. Yay! Here are 5 scores, and so we're going to find the standard deviation. The first step would be to find the mean. The second step is I'm going to subtract the 76, which is the mean, from each data point. So go ahead and do that, and then come back and check your answer with me. I have those 5 differences. Now my third step is going to be to square those, and once I've squared those, now I'm going to add and divide by 5. So go ahead and see what you get. When I added all the scores, I got 1056 dividing by 5. 211.2 is my variance, and then I take the square root of that, and it's approximately 14.53. Nice job. Now we have a different math class that took the same test. Why don't you go ahead, pause here, and calculate the standard deviation. If you're back with me, we found the mean again, 76, the deviations from the mean, the squared deviations, the sum of all those squared deviations, and then we're going to divide by 5 and take the square root. So the variance is 384 and the square root is approximately 19.6. So the second set of test scores had a standard deviation of 19.6. Now to analyze this, we consider both sets of scores. They both had the same mean, but they did not have the same scores. So the standard deviation shows the variation. The standard deviation for the first class, 14.53, and the second class, 19.6. So what does that tell us? Well, again, standard deviation is telling us how spread out it is. The scores in the second class are more spread out than the scores in the first class. Let's take a look at this example. Class A, the scores are shown. Class B, the scores are shown. That's what we had, and now we're adding a Class C. Do you think the standard deviation will be less than 14.53? Greater than 19.6? Between 14.53 and 19.6, or it's not possible to estimate? Yes, it's answer A, because those scores are much closer together than the scores of either Class A or Class B. So in summary, standard deviation measures the dispersion of data. The greater the standard deviation, the further the data tend to be dispersed from the mean. So we'll wrap up with standard deviation for today, and we'll move on to another method of analyzing dispersion of data in our next video. Have a great day.